talk about the voltage profile in the transmission lines. Here we have one grid that is connected to one bus bar here, 10.5 kilovolt. Then we have one transformer with the rating of 15 MVA, 139 to 10.5 kilovolt. You can find it from the library of the DIgSILENT. This is also same. And here we have 139 kilovolt and 10.5 kilovolt. And we have line here, 10 kilometer line, and the specification is 0.0251 ohm per kilometer and 0.122 ohm per kilometer for reactance, and the capacitance is 0.21 microfarad per kilometer. And the load initially here is 5 megawatts, so it's a simple transmission line. If you make a load flow, you can see here we have just 3% or voltage in the line. So here, if you click on this toolbox, we have the option as a transmission network tools. So if you click on the transmission network tools, you will have these options here, and the useful one is the PV curve calculation. So by using this calculation, you will see that by increasing the value of the power, how voltage of one bus bar will react. So for example, here we have terminal 2. If I run this PV curve, and then here we can see the PV curve plot for terminal 2. Here we can select any terminal that you want to see and execute. Here you can see this plot. So it says that now we have 5 megawatt load, and the voltage in the bus bar is 2.5% higher. So if we increase the load in P, because the current will increase, and for sure we will have some voltage drop by reactance and resistance of the line. So you can see how the voltage will drop. So if we increase to 45 megawatts, so we'll have around 1 per unit as a voltage. So if, for example, here we can see also, then we will have some overloading in the transformers. So for this one, you can see the impact of P on the voltage. And if you want to see how is the impact, how is the voltage waveform, voltage profile during this 10 kilometer, just make a load flow, right click here and plot. Here we have the voltage profile. So if you run the voltage profile, you can see that here we have 10 kilometer line, and initially in the beginning of the line we have 2.8% over voltage, and at the end of the line we have more or less same value. So it's a little bit increasing. The reason for this increasing is that we have low loading here. So because we have low loading here, then the capacitance of the line will make some overloading. So if we increasing the load to 15 and then run the load flow again, so we can see because the capacitance is high, so normally we have a little bit over voltaging through the line. So if you change this capacitance and reactance, this one will changing. So if we have no loading, we have franti effect normally, and the voltage at the end of the line will increase. And when we have the load equal to the surge impedance, it will be constant. And by increasing the load, this will come down and down.